Today we shall study an algebraic system called group, consisting of a non-empty set and G and a binary operation like circle dot defined on it, satisfying some properties. The theory of groups plays an important role in the development of geometry, number theory, cryptology, etc. The journey of group theory began in 1770, but the major development occurred in the 18th century. Joseph Louis Lagrange tried to find a radical method for solving a polynomial equation of degree n which is greater than 4. In doing so, he initiated the study of permutation of roots of an equation as a tool for solving it, and these permutations were considered as elements of group. The other major sources in evaluation of a group theory are number theory, geometry, analysis, etc. Now, what is the definition of group? What is the definition of group? Let G be a non-empty set. G be a non-empty set and a binary operation circle dot, that is a binary operation. Is defined on this G, and then G circle dot is called group if the binary operation circle dot satisfies the following properties. The first property is G is closed. G is closed under the composition circle dot. Second is circle dot is associative. Third is there exists an element E in G such that E compose A equals to A compose E equals to A for all A in G. And the last or fourth property is for each element A in G there exists an element A dash in G such that A dash compose A equals to A compose A dash equals to E. So this is the main properties of group. Okay. Now this group is called abelian group or commutative group in honor of Niels Abel if the operation or binary operation, that is circle dot, is commutative. That is suppose A and B belong to G, then A compose B equals to B compose A. Okay. Now this E is called the identity element, and this A dash is called the inverse element of A. Now here the question arises, can a group have two different identities, or same problem can be thought of in case of inverse of an element in the group? The answer will be clear from the next theorem. Suppose G be a group. With respect to the binary composition circle dot, it contains only one identity element. Let, this is the theorem, let E and F be two identities, in the group. Okay, then E compose A equals to A compose E equals to A, and F compose A equals to A compose F equals to A for all A in G. Now we have E compose F equals to F by the property of E, and also E compose F equals to E by the property of F. So from these two relations we can easily obtain that F equals to E, and this proves that G contains only one identity element, or G0, you can say G0 or G contains only one identity element. Okay, and now we have to prove that the group G0, in the group G0, each element has only one inverse. The next theorem is, in a group G0, each element has only one inverse. Proof is, let A belongs to G, okay, and A dashed and A double dashed be two inverses of A, then what happens? Then A dashed compose A equals to A compose A dashed equals to E, and A double dashed compose A equals to A compose A double dashed equals to E, where E being the identity element. identity element. Okay, now we have A dash compose A double dash, that is equals to, by associativity, A dash compose A double dash. That is, since circle dot is associative, okay, circle dot is associative, but A dash compose A double dash, that is equals to A dash compose E from this relation, that is equals to A dash, and from the right hand side, this A dash compose A double dash, that is equals to, from this relation, that is equals to E compose A double dash, that is equals to A double dash. So from this relation, this expression equals to A dash and this expression equals to A double dash. So from these two relations, we can say that A dash equals to A double dash, and that means it is proved that in a group G0, each element has only one inverse. So in this group G, A has only one inverse. Okay, and this completes the proof.